Welcome to Auto 155, Electricity and Electronics 1. My name is Tony DeBlasi, and in this lecture I will be covering series circuits, parallel circuits, and series parallel circuits. This is the first part of a two-part lecture based on Chapter 41 from the Automotive Technology Principles, Diagnosis, and Service 6th edition. For more information on this topic, please read the chapter and refer to the PowerPoint found in the course content folder. Please note that there are both audio and visual lecture attendance codes scattered throughout this lecture. Please write these codes down as you see and hear them. At the completion of this lecture, you will be required to go to the assignment folder and take the online lecture attendance quiz in order to get credit for attending this lecture. In this chapter, I will cover how to identify a series circuit. I will explain Kirchhoff's voltage law and explain how to calculate voltage drops in a series circuit. I will discuss the different series circuit laws. I will explain how to identify a parallel circuit. I will explain Kirchhoff's current or amperage law. We will review the different methods on how to calculate the total resistance in a parallel circuit. There are 5. I will explain how to identify a series parallel circuit where their two circuits are combined. And we will cover how to calculate the total resistance of a series parallel circuit. The information found in this chapter will help you prepare for the ASE Electrical Electronic Systems A6 Certification Test Content Area A. We will begin this chapter by talking about the series circuit. So a series circuit is a complete circuit that has more than one electrical load where all of the current has only one path to flow through all of the loads. So in other words, there's multiple devices, there's multiple components, or there's several loads that are connected in a circle. There's no other path for the current to go other than through each of the loads, one right after the other. So the circuit must be continuous or have continuity in order for current to flow through the circuit. So obviously we're going to be discussing how loads or devices or resistance are arranged in a circuit being series. We also have to mention that power sources can be connected in series as well. You can have two batteries in series. Switches can be in series with a load. Fuses can be in series with a load. But when we talk about a series circuit, we're actually discussing the loads themselves. In the last chapter, chapter 40, we spent a lot of time discussing how Ohm's law works and how to calculate either volts, amps, or ohms based on the other two values, knowing their measurements or knowing what their values are. We're going to apply that heavily in this chapter as well. So because all the current flows through all of the resistances, the total resistance, which we will refer to as RT, is the sum, which you would add all of the resistances together. Ohm's law can be used to calculate the value of one unknown voltage, resistance, or ampere if the other two values are known. So as a review, we'll discuss Ohm's law one more time just to refresh it. The amperage in a circuit is the result of volts and ohms. So once again, in order to get my amperage, I have to divide the ohms in the circuit into the volts. Now, obviously, Ohm's law can be switched around if we know the other two values through basic algebra. But once again, I want to find my amps, right? My amperage is the key. I want to find out how much current I have. So let's apply it. Here's a circuit with 3 bulbs, bulb 1, bulb 2, bulb 3. Notice bulb 1 is dropping, or it has 1 ohm. Bulb 2 has 2 ohms, and bulb 3 has 3 ohms. Because this is a series circuit, we have one essential pathway for the electrons to travel. They leave the positive terminal, they travel into bulb 1, where there's 1 ohm of resistance. They leave bulb 1, they have to go through bulb 2, there's no other choice. As it goes through bulb 2, it's faced with 2 ohms of resistance. It then leaves bulb 2, it goes down to bulb 3, where it's faced with 3 ohms of resistance before it comes into its return path back to the battery again. To find RT, which is total circuit resistance, to find RT in a series circuit, we have to add the ohms. So that's pretty easy math. 1 plus 2 plus 3 is 6. So we have a total circuit resistance of 6 ohms, or RT 6. We would then use Ohm's law to find out my current flow. Because I know I have 6 ohms of total circuit resistance, and I know my battery voltage is 12, I would divide the 6 ohms into the 12 volts to give me a total current in my circuit of 2 amps. So let's take a look at figure 41.2, I have eliminated a bulb. So there's only two bulbs now. So one resistance is eliminated, or one load has been eliminated. So now my total resistance is 3 ohms, because bulb 2 is 2 ohms and bulb 1 is 1 ohm. The current flow will now be 4 amperes, because my total circuit resistance, my RT, is 3. 3 into 12 gives me 4, so I have 4 amperes. The current flow doubled from the last example, so it's 4 amps now instead of 2. We cut the resistance in half. We removed a 3 ohm bulb. We left ourselves with an RT of 3 that doubled the amperage. So once again, this goes back to what I said in chapter 40 when I talked about the seesaw. As resistance goes down, amperage goes up. As resistance goes up, amperage goes down. So everything's related. And once again, you'll hear me repeat this 1,000 times. Amperage is the result of the volts and the ohms. That is Ohm's law. We spent a lot of time in chapters 39 and 40 discussing pressure and current and resistance, or voltage, amperage, and ohms. I figured I'd put the people who those terms are named after so you can understand where they came from. So Alessandro Volta was credited with inventing the first real battery. He called it the voltaic pile. It was made of zinc and copper and separated by a brine-soaked cloth, and essentially that acted as electrolyte. And voltage, or volts, are associated or named after Alessandro Volta. Andre Marie Ampere was credited with many discoveries and breakthroughs in the study of electromagnetism. So they named the ampere, which is a column of electricity, which we call an amp, which is 6.28 billion electrons passing a given point every second. That's named after Andre Marie Ampere, the amp. And then lastly, resistance, or ohms, are associated or credited to George Simon Ohm. He came up with the mathematical equation, Ohm's law, that we've been talking about, and is so useful to diagnosing electrical circuits. The reason I brought this up is that sometimes it's nice to put a law or a standard that we use all the time, kind of associate it with a face, because we cover a lot of these things in electricity. And the next one we're going to be discussing would be Gustav Kirchhoff. He had two major laws that we'll be studying here, and they're kind of out of order. The Kirchhoff's second law has to do with voltage. So his second law was the voltage around any closed circuit is equal to the sum of the voltage drops across the resistances. I know that might be a little bit to wrap your head around. I'm going to use plenty of examples to demonstrate what this means. His first law is his current law, which we'll get into a little bit later, has to do with parallel circuits. But his second law has to do with series circuits. So because we're going to learn series circuits first, his second law applies to that. Sorry for all of this numbering of the laws. You don't need to know this. You just need to know that these laws function. So just remember, he has a series circuit voltage drop law, and he has a parallel circuit current law. So before I get into the next example, the term voltage drop, which is an important term, you'll be using it quite a bit, applies to a live circuit, or a closed circuit, or circuit where current is flowing. What we're trying to do is determine the difference in pressure on one side of a conductor compared to the difference in pressure on the other side of the conductor. That pressure, being voltage, would be voltage drop. In this diagram, 41.3, we have one light bulb, which is our load. We have one battery, which is our power source, and then we have wiring, which is our conductive path. So we have our power, we have our path, we have our load. You'll notice there is a fuse inserted on the power side of this circuit. Now, what we're demonstrating here with these three measurements, we have a voltmeter here, a voltmeter here, and a voltmeter here. What we're measuring are voltage drops. Now, normally when you measure voltage, you're putting one lead on the positive and one lead on the negative, or you're putting leads on either side of the load like this voltmeter. But you can also put voltmeters in the stream, or I should say in power or the ground side wire. And when I say in the wire, we never want to pierce the wire itself, so we want to find points that we can actually do these measurements. And we'll get into things like what's referred to as back probing a connector, where you can slide a needle in to get your measurement, but you never want to pierce the jacket. We're going to talk about that extensively, but on a fuse, you can test either side of a fuse. So when current's flowing through here, your voltage drop should be negligible. Now this says 0. I'm not going to say it's ever going to be true 0. There'll be a tiny amount of voltage drop across the fuse, but we're talking millivolts. Not enough to affect anything. We do want all of the voltage to drop across the load or the resistor, right? So as the power flows into the bulb, the power side flows into the bulb, the ground side flows out of the bulb, the difference in pressure on either side of the bulb should be what the applied voltage is. And that's the applied voltage here. That's the applied voltage here. Likewise, if I were to measure the ground side of the bulb and put my other lead down at the chassis where this wire is connected, so essentially what this multimeter here is measuring, I should see negligible voltage drop, or in other words, 0 volts. To help make this point, I'm going to use a circuit simulator throughout this presentation because I like the animations to kind of show the travel of the electrons in the circuit. And I can also use a little multimeter to help me make my points. We notice current is flowing from our battery through a fuse or a switch. Then it goes off to the light bulb where it travels across the tungsten, and then this would be my ground side coming back to the battery again. So if I were to measure from the battery, I'll measure the voltage on the battery first. We'll see how we do here. So I have 12 volts on my battery, and disregard the fact that this says negative. This simulator works on electron theory, and in automotive we're dealing with conventional theory. So don't pay any mind to the negative symbol. Just know we have 12 volts here. Okay, so my multimeter is displaying 12 volts at the battery. If I were to measure out at the load itself, I'll put one lead on the load, on the power side of the load, and one lead on the ground side of the load. I have virtually, or just about, 12 volts. Now there's a little less. And the reason it's a little less is this is a very accurate circuit simulator because the wire itself has a tiny bit of resistance in it. As we said, everything has resistance, but the load has the most. Okay, so the load should drop a majority of the resistance. So if I wanted to see the voltage drop on my power side wire, I would put it on my positive terminal of the battery, and then I would put my other lead right over here at the switch or at the fuse. And you can see there's a tiny negligible amount of voltage that's dropping. On the diagram we just looked at, 41.3, it showed that it was 0. As you can see, there's always going to be a little bit, right? But it is basically, if we're rounding up, it's 0 volts. So if I put my lead on the other side of the fuse or the switch, you can see it's pretty much 0 volts. There's no voltage drop there. And based off of 41.3, if I put my lead on either side of the bulb, you'll see the voltage drop equals what's being applied. And if I take one of my leads, doesn't matter which one, I'll put one lead on the ground side of the bulb, and I'll put my other lead at the negative side of the battery, you will see that that number is virtually 0 or extremely low, which is what we want. That's a good functioning circuit. So once again, we can put our leads in any point on this circuit, and that will display voltage drop. Chapter 41, Lecture Code Question Number 3. Make sure to write this down. 33987. Once again, that is 33987. Please write this down. So as we look at figure 41.4, in a series circuit, the voltage is dropped or lowered by each resistance in the circuit. The higher the resistance, the greater the drop in voltage. So another way to think of voltage drop is used voltage. So out of these three resistors or resistances, these bulbs, bulb 1 has a 2 ohm resistor in it, bulb 2 has a 4 ohm resistor in it, bulb 3 has a 6 ohm resistor in it. So now that we've established in diagram 41.4 a 2, 4, and 6 ohm resistor with a 12 volt battery applying the voltage, let's run through the math to determine how to calculate the voltage drops per bulb. So we're going to apply Kirchhoff's voltage law here, his series circuit voltage law, which is his second law. Total resistance of the circuit is determined by adding the individual resistances. So to the electrons entering the circuit at the battery, they don't see individual loads in a series circuit. They see one large resistor. They don't see individual resistors. They see one large resistor. So we're going to add them together. 2 plus 4 plus 6 would be 12 total ohms, or an RT of 12. Now what we're going to do is we're going to determine the current flow. And that's easy to do. We're going to use Ohm's law. So 12 volts applied with a 12 ohm resistor, 12 divided into 12 would give us 1 amp. So there's 1 ampere of current flowing through that circuit. Our total resistance is 12 ohms. Our total voltage is 12 volts. And our current is 1 ampere. Since we know this, what we can do now is determine what each load or what each bulb is dropping, once again using Ohm's law. We would multiply the resistance times the amperage. So the voltage drop for bulb 1 would be the amps, which are 1 amp, times the 2 ohm bulb would give us a 2 volt drop. Bulb 2, because it has a 4 ohm resistance in it, we multiply it by our 1 amp of current that's flowing through the circuit. That gives us a 4 volt drop. Bulb 3, its resistance is 6 ohms. The amperage in the circuit is 1 amp. 6 times 1 is 6 volts. So it's a 6 volt drop. Before we move on, and we're going to talk about the circuit more, but what I wanted to do was I wanted to take the math that we just covered and apply it using the circuit simulator. So once again, this is bulb 1, this is bulb 2, and this is bulb 3. As you can see, this says 2 ohms of resistance in bulb 1, 4 ohms of resistance in bulb 2, 6 ohms of resistance in bulb 3. I'm going to use an ammeter to find out our current, right? So we have a 12 volts applied. If I move this recticle over the wire, that will tell me I have 1 amp or 1 ampere of current flowing through the wire. And that's the same anywhere on the circuit, anywhere I place this, that'll tell me what I have. Now what I'm going to do is verify. Our math just told us that bulb 1 at 2 ohms times 1 amp should give me a voltage drop of 2 volts. So if I put my multimeter on the bulb itself, we can see that we have a 2 volt drop at bulb 1. So our math has calculated correctly. So now what we're going to do is we're going to go to bulb 2. Put one lead here and one lead here. We should see 4 volts. Let's see what we get. We have 4 volts applied, or 4 volts being dropped. And then finally, we're going to move it up to our third bulb. 6 volts being dropped because we have 6 ohms times 1 amp would give us a 6 volt drop. Once again, our math was calculated correctly. We used Ohm's law to determine this. So if we go back to our presentation, now that we know this and we've confirmed this, that bulb 1 is 2 volts, bulb 2 is 4 volts, and bulb 3 is 6 volts, we're going to use Kirchhoff's law to prove out that adding the voltage drops will equal our applied voltage. 2 volts plus 4 volts plus 6 volts equals 12 volts. As he stated in his law, the sum of the voltage drops should equal the applied voltage, and that is true of a series circuit. Chapter 41, Lecture Code question number 4. Make sure to write this down. 87945. Once again, that's 87945. Please write this down. Now that we've used Ohm's law to calculate both the total resistance of a circuit, how to calculate the total current in a circuit, and also how to establish the voltage drops per resistor, what we're going to do now is apply that knowledge. We're going to do a knowledge check. I want you to find the voltage drops for this circuit, 41.5, pause the video, calculate it yourself, and then check to see if you got it right. So the voltage drops are, for the 4 ohm bulb, would be 8 volt drop, and for the 2 ohm bulb would be a 4 volt drop. This is how it was calculated. We add them together because they're in series, so 4 plus 2 would be 6 total ohms, or an RT of 6. So here's our answer, 6. We then take the 6, we divide it into the 12 volt battery. That gives us a total current for the circuit of 2 amps. Then what we do is we find the voltage drop per resistor. So 2 amps times 4 ohms would be 8 volts. 2 ohms times 2 amps would be 4 volts. Then we add the two voltage drops together to equal 12, which is also our applied voltage. At this point in the lecture, specifically for series circuits, I want to review 3 simple laws or 3 basic rules that we've already covered, but I kind of want to summarize them. Law 1, the total resistance in a series circuit is the sum total of the individual resistances. So as I said, to the electrons leaving the battery, they don't see several resistors or loads. They see one large resistor. Law 2, the current is consistent throughout the entire circuit. So at any point you measure, you'll always see the exact same amount of amperes. So if 2 amperes of current leave the battery, 2 amperes of current will return to the battery. The third law states, although the current in amperes is consistent, it doesn't change, as you can see in this example here, 2 amps all the way around, the voltage drops will differ, or they may differ, right? They could possibly be the same depending on the ohms. If the ohms are all the same, the volts will all be the same. But in this case, we have 2 separate or different ohmed resistors. We have a 2 ohm resistor dropping 4 volts and a 4 ohm resistor dropping 8 volts. So they're not consistent. So that's the law with series circuits. Amperes will be consistent, but the voltage drops may be inconsistent. As we wrap up the first part of our lecture on series, parallel, and series parallel circuits, we're going to review series circuit calculations. We're going to solve for total resistance in the circuit, current flow, and voltage drops. We're going to go through 4 examples to hopefully lock in the process on how to do this. In our first of 4 examples, example 1, which is figure 41.7, we need to solve for the resistor at the bottom of this series circuit. We don't know what it is. We need to figure out how many ohms there are. So in order to do this, we can start by finding total circuit resistance by dividing 3 amps into 12 volts to give us an RT, or total circuit resistance, of 4 ohms. So we know there are 4 total ohms in this circuit. Because we know that all of the resistors combined equal total circuit resistance, we do know the value of our first resistor. It's 3 ohms. We know that the total resistance is 4 ohms. We would just simply subtract the 3 ohm resistor from our RT of 4 ohms to give us 1 ohm. That's what's left over. So this second resistor, or R2 here, would be 1 ohm. In our second of 4 examples, 41.8, we need to find the resistance for R3. We know our amperage, we know our volts. We can calculate RT, which is total circuit resistance, which would be a total of 6 ohms. We know that we have 3 resistors now instead of 2. We would add these together. That would give us a total of 4 ohms. We would then subtract the 4 ohms from the RT of 6, leaving 2 ohms for our R3 resistor. In this example, example 3 of 4, 41.9, we need to figure out how many volts there are being applied to the circuit. We can start by adding all of the resistors. So 1 plus 1 plus 1 would be an RT of 3 ohms. We know that we have a 4 amp current pulling through this circuit. So if I have 3 ohms and I have 4 amps, well, Ohm's law, we multiply them. 3 times 4 would be 12 volts. In example 4, 41.10, we need to know how many amps of current are flowing in the circuit. So before we can find that, we need to know how much resistance we have. So once again, we need to find our RT by adding all of the resistors. 2 ohms plus 2 ohms plus 2 ohms would be a total of 6 ohms, or RT of 6. We would then use Ohm's law and divide 6 into 12 to give us our total circuit current of 2 amps. This concludes the lecture for the first part of Chapter 41, Series, Parallel, and Series Parallel Circuits. For additional information on this topic, please read this chapter and refer to the PowerPoint found in the course content folder. Now that you have completed this lecture and you have written down the online lecture attendance codes, please go to the assignment folder and take the online lecture attendance quiz in order to get credit for attending this lecture.